All right, good afternoon. Good afternoon, everyone. This is Celso Batalha, Shoten, and let's initiate this conversation with the main topics we have been discussing the last 2 weeks or so, and that has to do with the tools astronomers use in order to find out what is out there in space. Since astronomy is probably the only science we really don't have at hands the object we studied, or most of them, or the majority of the objects. We don't have quasars in our laboratory or galaxies, they are too big, and certainly we have not yet bring a piece of dark matter to our laboratory, although we have candidates so far. So photometry and spectroscopy, as you guys have well placed in our discussions, are the basic tools astronomers, or constitute the basic tools astronomers use to develop and build up knowledge. And photometry, and I would like to show here the web page of Kepler satellites, and that was one of the topics indicated in this past week discussion. So Kepler was able to find out about the existence of over 3,000 planets encircling stars other than the Sun. So those are exoplanets. And using photometry, basically. So the technique is here depicted. So you have a photometer that is sitting in a satellite, Kepler. This is a space satellite, and this photometer keep looking at a region in the sky 10 by 10 degrees. It's like a fist at arm's length projected in the sky in the constellation of Cygnus. And what it does, once if the system star planet is such that as the planet encircles the stars, it crosses the view of the star disk, like the simulation here suggested, we see a small dimming of the star brightness. And this is a dim as small as it can be. The precision required here is 1/1,000 in magnitude. And I would like to point to you one of the web pages if you are interested in doing a little research as a citizen. There is a project called Planet Hunters. And the Planet Hunter, if you have computer time, especially this is good also for teenagers, if they want to get their hands dirty with some real research and help scientists to find things, they can become a member of the Planet Hunter community. And what they do, they took all this Kepler data that has been analyzed already, and all these several thousands of candidates and 3,000 planets that have been discovered. They are, in fact, the result of photometric campaign of Kepler. And here's what I'm displaying is what Planet Hunter do. I mean, the software is able to pick up on these obvious signals, as you can see in this curve. So this is a tutorial that helps you to introduce you the technique of planet detection. So you have each one of these dots represents the stellar brightness observed over a time scale of about 30 minutes. So all the intensity is set up, and then you have a point, and that point is further normalized to a standard, to a reference. So here is 1 point. And now, if a planet starts to go into the stellar disk, you see a small dimming of the total or overall stellar brightness. And you see it's is what? So it goes from, oh, wait a second. So these are other gaps in the light curve. So it goes from 1 to 0.9907 in magnitude. So the software can be intelligent enough or smart enough to detect these falls, but it's sometimes it doesn't. So it doesn't get this signal. And then what Planet Hunter do is to allow people like me and you, citizen, that would that has computers and free time to help classify light curves. So what they do once you sign up in the site, it sends you uh, a light curve, and then you visually inspect the light curve for this dimming process. And once you find, you classify them as being probably a binary or a binary system, two stars encircling one another, and the signature is different from that of a planet. The magnitude fall or the brightness fall is much more intense than that of a planet because stars are bigger. And then you train yourself to just by visual inspection to identify possible candidates for planet search. And then you send that information is sent automatically to whoever is organizing this project. And if the planet is further confirmed, then your name become part of a scientific paper. So it's an interesting things. But basically, what is being shown here is one of the applications of photometry, which is this technique that only does is to be able to collect light intensity over time, and then you analyze that, and then you try to identify what is exactly being responsible for the light curve fluctuation. So the other technique, which is spectroscopy, as you saw, is slightly different. What it does, it takes the light curve and creates a rainbow of it. And then when you look in detail on that rainbow, you find, in most of the cases, absorption lines. And astronomers down here on Earth were able to classify with very good precision from which atoms and transitions those lines are or represent. And by doing so, when you observe these stars, you can not only identify what's the chemical composition in the stellar atmosphere, but also at what rate the star rotates, what sort of a turbulence or um, interactive mechanism or activity, magnetic activity the star is going through, and all projected velocity, all kind of things. So it's a fascinating subject, and off and on in as the class progress, I will call on any of those two techniques to explain how we collect data. Basically, that's what it is. Okay. Um, Also, this week we have a discussion which is based on the article, and the article is Measuring Star Properties. No, that is right here. March 13, that's March 20. Astro News 4. It's funny, I thought it was a different one. Although this is good. Let me see if I'm getting the right one. Just a second. Just a second. That's March 20. Yeah, that's today. March 20, Planetary Evolution. Yeah, The Seeds of Science Skepticism. It's funny, I thought was another one. On dwarf galaxies. Apparently not. Am I in the right course? Yeah, yeah, I am in the right course. Okay, so yeah, science of this seeds of science skepticism. Interesting. So I have to think about it. I thought I got a wrong seed. So let's see what is in there. Planetary evolution, that's here. Um, January 30, March 6, March 27. Oh, there you go. Oh, no, I'm right. I knew that. Somehow I collapse and I miss it. But it's dwarf galaxies, Astroneu 3. So the article is this article you have to read and then do a brief review and find what sort of instruments were used to do this type of research. But this article is based on the fact that later on we are going to learn about galaxy formations, and in one of the models presented when in fact 10, 20 years ago, um, we would read in books that dwarf galaxies would be the most populated galaxies in the universe, and simulations done 20 years ago or so would indicate that when spiral galaxies like our Milky Way happen to be formed, and after the Big Bang, then it would be surrounded by thousands of these dwarf galaxies, and it was suggested that dwarf galaxies were in fact the most populated galaxies in the universe, and then when we look at our Milky Way galaxy, there are a few dozens, right? Not a lot. Our local group of galaxies include Milky Way galaxies, Andromeda Galaxy, which are relatively big, and a few dozens of smaller dwarf galaxies. So when now with powerful telescope, you look at clusters of galaxies nearby, and the percentage of dwarf is not that great. So why is going on? And so the point of the article is to come up with a new approach to solve the problem that includes dark matter, and so it's a way to introduce this important subject in astronomy to you guys. So dark matter and the simulation this group did on galaxy formation. So it's interesting to see how these galaxies, how this simulation form. Now, the seed for discussion is the force, the field responsible for galaxy formation is also the field responsible for the formation of a star, which is the subject of today's class. What I would like you to do is to draw parallels between the formation of a star, the formation of a planet, and the formation of a galaxy. So galaxies are a system of hundreds of billions of stars. A star is a system that might have dozens or more of planets and millions of smaller systems going around. Um, and the formation of the planet, or protoplanet formation, as we learn, is also surrounded by a center planet, and depending on the mass, with a large concentration of smaller objects going around. So the point is, and that's the point or the seed of our discussion, is first of all, which field, which force is responsible for the formation of these three different major systems: planet, star, and galaxy. That's the first thing. And the second, I would like you to give parallels. To say, okay, so a star, when it forms this, this, and that. Galaxy also, when it forms this, this, and that. Same thing with the planets. If you can add figures, that would be great. But you can add words for that. Good enough? Oh, Julius. Hey, Julius. I have my good students here. is increasing now. The population of students attending the chat is increasing 50% or so, 100% in fact. That's great. All right, so let's go to the main topics. And there you go. Planetesimal. So this is a word that's going to be following us, and I would like to show a simulation of planetesimals, and I had that in the other area, but it got screwed. Just a second, let me pull up dx_lupi. I think I already showed this before, but I'm going to show it again because it's a nice way to explain the action of gravity force on star formation.
The fading light of a flaring.
So let me stop here. Okay. So here's a circumstellar disk. So when the star formed, we have gravity that collects material spread over a few light years. And if the density of this gas is good enough, then gravity will take it in and will be able to overcome the gas pressure that exists in the interstellar medium, and then collapse or contraction takes place. But that is not the only story, and in fact, this could be used as a seed for discussion. So, in addition to gravity that brings gas into a center of mass, all this either, if you will, proto-galactic material or protoplanetary material, protostellar material, they all have their own initial rotation. And astronomers refer to that as angular momentum. So the gas is not kind of without and devoid of motion. It has motion, it has a small rotation. And as the gas falls in, it also rotates, and it's, as we say, angular velocity of gas at certain location. As the gas contracts, it increases. Is the ballerina effect. And what you're seeing here is a stage in stellar evolution where the gas, as the gas falls and in fall towards the center of mass, it gets a point that is more efficient for the gas, instead of falling directly towards the star, to fall on the disk, which coincides with the equatorial plane of the future star. So the gas falls on the disk, and then from the disk, and following Kepler's law, it falls onto the star in a process we call accretion. And then as the gas migrates, spiraling into the center star, it loses energy and momentum, and that is transferring out to the entire disk. So what I would like to show here is pretty much this rotation in one star that has let me see if I can get some more picture here. I just want to get the animation. There you go. We are not there yet, but as this process evolves, eventually the star enhance its magnetic field process, and that's, let me stop here, its magnetic field activity, and as a result, it forms a gap. It forms a gap between the star and the disk itself. See, the disk doesn't go straight to the star. It stops at certain distance, and from there, the stellar magnetic field is the one responsible for bringing this gas from the disk onto the star, and is usually brings that to high latitude and low latitude regions. I mean, those details we are not going to cover, but suffice to say, there is lots of little detail going on. But the main reason is the gas eventually spirals and fall towards the star. In our solar system, when as well in other stars, the gas in the circumstellar disk eventually coalesce and eventually cools down, and then crystals and grains start to be formed, and it allows and favors another process we call also accretion. Accretion is any process by which mass grows as a result of a driving force. So this animation here is showing accretion, which is driven by gravitational field. So gravity is responsible for that. But you have a different type of accretion when these little grains you see in this picture start growing in size as a result of accretion driven by electrostatic forces, basically. Like when you have two grains, they become electrified and then they stick together. And this sticking together just allow them to grow in size. And in few million years, simulations indicate in few million years, then encircling the star, all these planetesimals, this big chunk of material, are already in place. So this is something I want to show you. There are other details which I'm not going to go there now. Let me get out of there. Yeah. See if I can find it now. Solar. And I had to collect that animation. Oops. Okay, that one. So this is another interesting video that also indicate formation of solar system. And let me see if I advance here. Here's an example of one of these planetesimals. So one of these objects formed as a result of accretion, to the point that eventually when they become big enough, a different driving force takes place, and that is gravity. So when they become sufficiently massive, then gravity will be a driving force attracting more and more objects onto them, and eventually they grow in size because of gravity, basically. More example. Here's an example of an accretion disk. You have the central star, and as I mentioned previously, the material that formed this stellar system, in fact, was spread over a few light years, and then the gravity force just brought all of that to a center part. But after this gas is sufficiently contracted, then this, and as a result of the angular momentum, or this energy associated with rotation, which is conserved in the system, then all the gas will prefer to fall onto the equatorial plane and then migrate following Keplerian laws to the center star. And that's what we are seeing in the simulation right here. But all of this is gravity, basically. All of that is gravity. Now, you can see Kepler's law at play here in the following example. Let me highlight that to you. If you look closely, the rotation rate of the gas closer to the star is faster, or is higher than it is in the outer regions. You see that? In other words, the center part rotates faster than the outer edge. And that is a result of Kepler's law. So this is a Keplerian disk, and So eventually, that's why Mercury goes faster than it does Uranus or Neptune. So here's a simulation indicating how these planetesimals formed. First with seeds, crystals here and there, and then eventually they grow in size, and eventually you ended up with a collection of planetesimals. Let me just speed up here. Now, planetesimals closer to the sun, and because of this star is hot, so dust, think about it. So you have this star that is hot, and you have a disk that is sufficiently not as hot as the star. So the disk is hot closer to the star, but is 1,000, 2,000 Kelvin temperature, so it's not a lot. But the gas closer to the star, the gas closer to the disk, is exposed to heat and also to solar wind. So what is the main consequence of it? So the main consequence is that crystals formed closer to the star will not be crystals of volatile materials such as methane or nitrates or water, ice or carbon dioxide. So you have closer to the star, the conditions will be such that it will favor formation of iron oxides, metals, carbonates, uh, and further away in the outer edge of this disk, it will favor ice formation. So when we think about planetesimals, and as you go through this chapter, pay attention to two important formations or planetesimals. One is called asteroids, and the other one is comets. So they are solid, but they have a different chemical composition. So asteroids are the remain of planetesimals formed closer to the sun, and they are not ice-rich objects at all, as opposed to comets. There are dirty ice balls that has both types of crystals in it, volatiles and pretty much metal oxides or carbonates, and they are different. Now, this part of the simulation show what happened in an early history of our solar system when big Jupiter and big Saturn, they start slinging shot with these planetesimals. And that's what you see when the animation is speed up, or better saying simulation. So they start slingshot all these rocks, most of them comet nucleus, all over the solar system, and two regions were the recipient of most of these chunks. One is called the Oort cloud, which surrounded the entire solar system at more than 50,000 astronomical units all over the place, kind of a spherical bubble that we are in it. And another region was a Kuiper belt, where supposedly Pluto and Eris and all these most of the dwarf planets are supposed to be members. So eventually, Saturn and Jupiter stopped migrating, and all these link shot of volatiles ended. Now, what's interesting, if you look at water in our own planet, some claims that a large percentage of this water came from that region, slingshot by these giant planets. So that's so much for the simulation. So let's browse through meteor showers. So meteor showers are, our planet increases its mass regularly every year because of these debris that falls on it. Meteor showers or shooting star, they are not shooting star. In fact, they are pieces of debris. Some of them are stony rich, some of them are metal rich, that falls on our planet. So at night we can see them because they burn out and they form some visible, they do a visible display in the sky. Now, meteor showers is when you have a large fall in per hour, and they tend to come from the same region in the sky, the same constellation. So the Leonid is a meteor shower that originates in the constellation Leo and is associated with, I mean, meteor showers are in general associated with the tails of comets. As they approach the sun, they release gas and comet and dust, and leaving a trace of dirt things that when Earth goes through that path, Earth and again, gravity force brings them in, and then you see them just falling. So they are not stars. Shooting stars are not stars. They are pieces of debris, 1 grain size. Thor, I know you were saying something, but I can't hear for some reason. Oh, he might not be talking to me. Okay. Meteor showers. You can, there are now with everybody carrying cameras everywhere, it's not difficult to find it's not difficult to find somebody filming one of those. That's a good one here.
Creative thinking and smart partnerships are lifting New York's southern tier.
We've got talented manufacturing combined with...
No, I don't want to stay 15 seconds just to see that. I mean, you can, no, another one. Anyway, so if you have time, you can, oh, there you go. Let's see if I have a 15 seconds. My computer is so slow. No, I'm not gonna go there. But yeah, it's a common situation. Now, most of the meteors that you found in museum are iron rich, and the reason is because it's easier to find. We go with a metal detector, and then you can find them, as opposed to stony rich, which are not so stony rich. They are the concentration of iron is less than rocks or rocky material, kind of silicates or carbonates, and so it's more difficult to detect. But in the outer space, not outer space, in the intersolar system space, interplanetary region, most of the debris that are out there are stony rich, not iron rich. And the reason is these big planetesimals, they might differentiate in such a way that the internal core of them are more rich in iron than it is the outer mantle. So when they collide, this outer mantle more likely spread pieces of stony material out there, and not so much the iron center part. So the percentage of debris, stony rich debris, should be larger than the iron rich debris. Although it's easy to find them, the iron rich debris on ground, and we call those meteorites because of metal detector, basically. And especially in Antarctica, right? So you go with drones, you can just fly over and find little craters caused by this impact and collect them. Or if you fall in your house or in your car, probably insurance company will not pay for. But if it's a stone rich rare, you can sell and make good money and go to the news and become famous. As they penetrate the atmosphere, they burn out, and that's the characteristics of one of them. Okay. Here is the basic steps in star formation. So you have a cloud called solar nebula, and you have to have a density or a concentration of gas that allows gravity to overcome gas pressure, basically. So gas pressure tends to expand out the gas, and gravity tends to bring the gas in. So we have these two opposing forces acting all the time in the gas surrounding the galactic center. So in certain regions, if processes that help to concentrate the gas occur, it might trigger or initiate star formation. Like, for instance, a star evolves, an old star evolves, explodes, you have a supernova explosion that generates shock waves that goes through the interstellar medium, and then you have a shock waves concentrating the gas in certain region. That concentration triggers or initiate this further collapse of the cloud, giving rise to stars. So supernova explosion can initiate star formation. That's one example. Another one is if you have the gas that pass through the density waves of our galaxies, and we are going to explain this later on when we study Milky Way. Now you have a region of higher density, and that triggers star formation in large scale, by the way. So there are several mechanisms that helps to trigger star formation. Another one is if the gas can radiate energy out of, if the gas has enough grains formed for some reason, grains might radiate energy away, which helps and favors star formation. So there are processes that leads to star formation, and that's slide number one. So slide number two is when, okay, eventually the gas realized that the cloud itself had some original rotation, and that rotation speeds up or becomes obvious and conspicuous with this circumstellar disk formed around the star. Now, in slide number three, you have some further development of that one with protoplanets being formed. Now you understand why most of our A planets in our solar system, they are more or less aligned with what we call ecliptic plane, which Earth orbital plane. I mean, the planets are formed not in crazy regions, right? Like in one of the Star Trek shows, The Next Generation, I don't remember which crew member was, I think Data or the captain, they were intriguing by, in one star system, the planet had some crazy orbit, would go kind of a polar one and then turn around and go equatorial. So in general, the telltale is once you form a star, and once you have a circumstellar disk, planets will be formed in the region where the circumstellar disk was. And that's why once the planets are formed, they will be encircling the star the same way always. So in other words, if you allow me to write here, there you go. So you form the star, right? And the circumstellar disk, all the other planets, oh, they don't cross orbit like that, but it's because I have a bad one. So they will be encircling the star in the same direction, basically, like a bunch of material. And also, if a planet like Jupiter have its own host of satellites, their satellites will be rotating and orbiting the same way. The planet itself rotate around its axis the same way. Like the sun rotates in the same direction. It takes about 25 days to complete one orbital, one rotational, one spin, in the same direction as the one Earth goes. And there are small exceptions like Venus. Venus orbit the sun in the same direction as the other planets, but spin in the opposite direction, probably because of collisions in the early stages of its formation. And collision, as you can see in slide number 4, with all this junk in there, all these planetesimals might be something very common. So this slide here it gives some clues as to why planets, as you move away from the sun and out to Neptune planet, they have less and less metal oxides. So closer to the sun, and because of the sun's heat, metal oxides, dirt, can be formed. So this rocky material can be formed, can be crystallized, and so you have olivine. Olivine can be formed in regions where Earth is. Now, Earth still forms olivine in the mantle inside Earth. In fact, in the asthenosphere, when subduction occurs, in fact, not so much in subduction, but where hot spots are formed, olivine, the crystal olivine is formed. It requires 1700 degrees Celsius to be formed. In the circumstellar disk, it's different. This olivine crystal can be formed as a result of UV radiation also coming out of the sun. But the main point is there is an optimum region where these crystals feel good to be formed and to grow in size and forming planetesimals with their characteristics. But as you go away from the sun, the region gets cooler, and then those metal oxides can be formed, but also ices will be formed. So you do not have ices, for obvious reasons, formed much closer to the sun. So Earth has some volatiles, has water in there, but not a lot. It's not the main characteristics. Here's one of the aspects of light. So light shining, sunlight shining on Jupiter reflects back with different characteristics. So this is how astronomers know about things without collecting materials. So you have light of the sun that has all the possible colors, and different parts of Saturn absorb light of a specific wavelength to power their chemistry. Same thing with circumstellar, not circumstellar, circumplanetary disk, the ring. But it rejects certain other type of light, like methane might be a little bit. That's why you have some blue being reflected off the ring, and different colors being reflected off different places. So the colors are false. So it doesn't mean that if you take a spaceship and you go there and look and you're going to see Saturn that way. But you can use different techniques to give different coloration to different aspects of light being reflected off different places, indicating the chemistry there, the temperature or the conditions are not the same. And here is the last picture I would like to show, and that is from planetary circumstellar disks, like the one I initiated this talk, that is common in EX Lupi. So here's an edge-on disk, and this is a protoplanetary disk in the Orion Nebula. So you might have some planet there being formed. Another one here is a protoplanetary disk around HL Tau, is a central star, and then you eventually have the star or the planet being formed and clearing up a gap where the material was. So the material in this gap will end up being part of the planet itself. Only now we have ways to observe that. The fact that planets were part of the circumstellar disk around stars came up in the 1800s. That was an idea, but only now technology advanced to the point that allow us to see this type of things. Here is your book. Spent some good time explaining Kepler results. Kepler is a space satellites that use photometry to find planet candidates out there. The advantage of Kepler is to be pointing the same sky region for several years, and as a result, it has accumulated a wealth of data that now is put it to the public. I mean, the Planet Hunt project that I showed to you in the beginning is a good thing to do. Is really, if you have kids, you can kind of initiate and make them curious about science. Put them in contact with this project, because once they do, and once they find interesting things, they can start talking to professionals that are working in the field, and that makes a big difference. So Kepler found that most of the planets out there are not like Earth or not like Jupiter, somewhere between. That's where most of the planets are located. They are not exactly in the habitable zone where water exists, but they are super Earth type of planet. And then you have all these different planets. So if the planet has not a lot of mass, the gravity is not going to be that great. Like in Mars, doesn't have a lot of mass, but has at a certain part in its geological life, it was active and formed volcanoes. Volcanoes are enormous because of lack of gravity as we have here on Earth, more massive of a planet. So that is stellar evolution, and again, not stellar evolution, but formation of a star. And when you studied stellar evolution, we will retake some of these materials or some of these ideas, especially when we study galaxy formation. All right. So I will stop taping now, and so I can talk with you guys.